we have talked about some basic reactions about coordination compound, also metal carbonyl compound. Remember, we have talked about the basic, metal, let's use X. Then it will react with L prime. So we have this type of, we call ligand exchange, right? And also when you have metal carbonyl, so metal carbonyl can have, nucleophilic and also electrophilic attack, reactions, okay? Then I'm going to show you several new reaction model we can observe for organometallic compound. So they are very important. Okay, you will understand why they are important when we talk about homogeneous catalysis using organometallic compound or coordination compound. Okay, so I'm going to show you some other very cool reaction model for organometallic complex. Okay, so all right, so the first one we are going to talk about two kind of reversible reaction model. So we call the oxidative addition, or the second one is reversible reaction, reversible model. We call that reductive elimination. So what's the oxidative addition? So what oxidative addition means, when you have a normally it's 16 electron transition metal compound. When you react with a substrate, so what happened is this transition metal can break the AB bond for a substrate. Then you form two new bonds, MA bond and MB bond. You break one bond from two new bonds. Okay, so accompany with this reaction, so we can observe two other major changes. So one is oxidation change with transition metal. Okay, so here if you have N here, then after oxidative addition, so the oxidation state of metal will increase by 2. At the same time, if you look at the coordination number, so you also see the coordination number will increase by 2 for the transition metal, right? That's obvious from this reaction. Okay, let's show you some examples how this oxidative reaction works. Okay, then just to point out, if you reverse this reaction, okay, you end up with we call reductive elimination reaction. Okay, so you decrease oxidation by 2, you lower the coordination number by 2 for transition metal. What happened is you convert MA bond and B bond to AB bond. You form less electron rich transition metal compound. So the ending product here normally the 18 electron species. Okay, let's show you an example for oxidative addition. Okay, so here is a diphosphine dimethyl platinum compound. So what's the electron counting? Okay, how many valence electron here? Okay, then how many valence electron here? So for the just remember electron counting. Okay, then what happened is, so this square planar platinum compound will react with this methyl iodide. Okay, it will cleavage this methyl iodide bond. So you end up with this with this octahedral product. Okay, octahedral product. So you start from here is 2 plus, right? So that's because this minus ligand. So your platinum is 2 plus. Okay, then your ending product here, you get 4 plus. Okay, 4 plus. Okay, 4 plus. So you can say your platinum not only increase 2 plus for the oxidation state also increase the coordination number by 2. Okay, right now it's 6 coordination. And here is, 4 coordination. Right, so that's oxidative addition. Okay, let's show you an example for reverse model reductive elimination. Okay, so in this case we start from this 6 coordination rhodium dihydride. Okay, that's a rhodium dihydride. Okay, so here, so what's the oxidation state? Because the minus, right? So other phosphine are neutral ligand. So here is 3 plus. Okay, then it can undergoes the formation of hydrogen. So you form HH bond here. Okay, they form HH bond here. You remove 2 rhodium hydride bond here. You form HH bond here. So you end up with this rhodium 1 plus product. Okay, that's plus 1 product. Right now it's 4 coordination. Okay, that's reductive elimination. So normally we use RE to indicate reductive elimination reaction, and oxidative addition we use OA to indicate. Okay, so that's the first Nether reaction for them. Okay. So those are 2 reaction model for transition metal complex. Very important, very important. So we will see why they are very important in our next class. Okay, next class. All right. Here is another reaction model. We call that insertion reaction. Okay. So that's what's the insertion reaction? So insertion reaction means, so you have one ligand, okay, and let's see, so like this ligand, okay. Also we call that, normally we call that migratory insertion. So what does that mean is, you have, like in this case, you have this transition metal carbonyl with the X ligand. X ligand, normally that's a minus charge. We call that it's a nucleophile. So this nucleophile, remember, similar as the reactivity for metal carbonyl. So this carbon here is kind of, has some positive charge effect after coordination. So this X ligand can attack this carbon here. Okay, that's carbon. Okay, that's carbon. Then you end up with this, acyl ligand. That's type still acyl ligand. Okay. Okay, so the effect is you have X migrate to attack the carbon here, and in the same time we can view this reaction as the CO ligand insertion between metal and X here. Okay, that's why we call that migratory insertion. We simply simplify that as MI reaction for transition metal compound. Okay, so here you can see that's, we call that 1-1 insertion. So that's 1-1 insertion. That's 1-1 insertion. Okay, then also we have give you another example. Okay, so that's a real example. That's an example. Okay, you have this manganese pentacarbonyl methyl compound. Here it's nucleophile. That's the intramolecular nucleophile. Okay, so then what happened is, so you are going to be the methyl will attack the one of the carbonyl ligand. You form this methyl acyl ligand. Then the open site, you create an open site here, right? So remember, you create an open site here. This open site in this case is picked up by a CO from reaction medium from outside. Okay, so you form this product. Okay, and also we have another insertion model. We call that 1-2 insertion. So And what's a 1,2 insertion? So let's go back one more time. So one insertion is, and you just, that's if you, that's your, first place, right? So if you look at this carbonyl, if you look at one, that's you label the oxygen as the second atom. So actually, the X ligand attacked with the first atom. So we call that 1,1 MI reaction. Okay. So we also have 1,2 insertion reaction. Okay. So what's a 1,2 reaction insertion reaction? So in this case, okay, if you have this metal X attached with a alkene ligand, so then same thing, the X will attack with one carbon of this alkene ligand, then you end up with the X attached with the second carbon here. So that's in this case we call that 1,2 insertion. Okay, 1,2 insertion. So if you reverse 1,2 insertion, so we call that beta hydride elimination, because here this carbon is alpha, so this carbon is the second carbon. Also we can call the beta carbon. So the beta carbon, the hydrogen and the beta carbon can goes back to the metal, become metal hydride. So resume this alkene ligand here. So we call that as a beta hydride elimination. Because it goes back to the metal hydride alkene ligand compound. Okay, so let's show you some examples. Okay, so in this case we have this 1, 2, 3, 4, 5. That's a 5 carbon based alkene ligand. So with a metal hydride here, so we can do 1,2 insertion, right? 1,2 insertion. What happened is, so that's the first carbon here, second carbon here. So then here, sorry. So we define here as first carbon because your hydrogen hydride attacked this second carbon here. So you have 2 carbon between these two insertion into this 2 metal hydride bond here. So that's why 1,2 insertion. Then what happened is, you see, and this metal hydride, this hydrogen with the second carbon can goes back from metal hydride. Okay, metal hydride. But you will see, when this time we have the hydrogen, we can, if we let this hydrogen goes back, we will go back to this side, right? Same rectangle. But however, right now what happened is you are going to have same beta hydrogen from this side. So that's alpha carbon. Let's do. So this is beta carbon. So here is also beta carbon. What happened is this beta hydride can also attack this, can go back to metal. Then what end up with is, you end up with the alkene bond between these 2 carbon right now. Now that's the internal alkene. We call that's internal. That's the internal alkene ligand. But your initial reactant is a terminal alkene ligand. Okay. So in this case, you see we combine the 1,2 insertion and beta hydride elimination. We can do what? We can do alkene isomerization. Okay, so that's a power transition metal. So you will see, I hope you, from this example, you can see the power of transition metal to change the bond for a substrate, change the bonding model for the substrate. So that's a important game of homogeneous catalysis. Okay, all right. So I have showed you a number of important reaction activity for transition metal compound. Then I'm going to show you next lecture how we combine them together to deal with cool catalysis for transition metal compound. All right. See you next lecture, okay?